perimeter of G, and I assume the same assumptions. So G acts asymmetrically on a hyperbolic space, is either elliptic or hyperbolic. Well, the proof is very easy. I mean, the explanation how it follows from this theorem. Very easy. Apply the theorem to the case of the cyclic subgroup. Acting on this space X. And then this cyclic subgroup is either elliptic, in which case the element is elliptic. It cannot have general type action. The reason is that if you have two loxodromic elements here, then you can play the standard ping-pong game. So the consequence of this is the free subgroup on two generators embeds into G. You have a group acting like this. You can always construct a free subgroup there. So here you cannot have free subgroups, so this possibility is impossible. Therefore, it's either virtually cyclic, in which case it contains a loxodromic element. So the power of G is loxodromic, therefore G is loxodromic, or it's elliptic. So original Parane's proof was different than, but you can derive it from the theorem. Yeah, one more thing. So we did compare this theorem to the general classification. We didn't compare this theorem to the classification of geometric actions. So this is stronger, but only a little bit stronger. What's better here? You have the same three kinds of actions, but in addition, you have an algebraic characterization of elliptic actions. So G is always finite whenever it acts elliptically, which is not the case here, because every group can have an elliptic action on an elliptic asymmetrical action on a hyperbolic space. Just take the action on the. Okay. So, well, now we can define the notion of an asymmetrically hyperbolic group. The group G is called asymmetrically hyperbolic if G admits a non-elementary action, asymmetrical action on a hyperbolic space. So we do want to assume some sort of non-elementarity because otherwise every group is in this class. Equivalently, you can request that G admits an asymmetrical action on a hyperbolic space with unbounded orbits, and G is not virtually cyclic. That's because of this classification. So, equivalent. If you don't want to define what non-elementary means, then you can give that definition. Now, this definition is extremely difficult to verify because for some groups, there are no natural objects, natural hyperbolic spaces on which they act asymmetrically. For example, for out effect, there is no natural, well, it's not known whether there exists a natural graph like the curve complex for mapping class groups on which it acts asymmetrically. So instead of verifying this definition, people normally verify another definition. So let me give you another theorem which gives two more definitions which are more useful. And the theorem is the following. For every group G, the following conditions are equivalent. First, G is asymmetrically hyperbolic. So AH is my abbreviation for asymmetrical hyperbolicity. Second, G acts as a non-elementary action on a hyperbolic space with a loxodromic WPT element And let me stop writing the theorem and explain what WPD elements are, although you already have this definition. So an element G in G, so my group G acts on a hyperbolic space, an element G in G is called WPD, or satisfies weak proper discontinuity condition. So WPD is the abbreviation for weak proper discontinuity, and this condition was invented in a paper by Mladen Despina and Koja Fujiwara about mapping class groups. So G satisfies the WPD condition if for every base point x in X, so it's like a cylindricity, but only in the direction of axis of G. For every x in X, for every epsilon greater than 0, there exists m natural number such that now you look at the number of elements f in G such that the distance in X between X and Fx is small, most epsilon, and the distance in X between G to the n X and F G to the n X is also small. So this distance is finite. Sorry, this number is finite. Don't require any uniformity here, just finite. So the picture is this. You have X here, and here is the axis of G. Let's think for simplicity that G fixes some line and acts as a translation of that line, and X belongs to that line. Without loss of generality, we can assume this because this definition is independent of the choice of the base point. So then G to the n X, because G is a loxodromic element. Well, G is not a loxodromic element here. I don't need to assume that, but when we apply this, we will apply this condition to loxodromic elements, so G to the n will be far away. G to the n X will be far away from X. And then you have this standard asymmetry thing. So this is Gx, and this is the most epsilon, and sorry, Fx. And this is F G to the n X. So this is at most epsilon, and there are only finitely made such areas. So first of all, there is no uniform bound involved, so it's just finite. And second, you have to verify this condition just for one element, which is much easier. So that's why this is more useful. And third condition here in this theorem is that there exists a generating set X of G such that the corresponding telegraph gamma Gx, that's my notation for the telegraph of gamma of G with respect to X, is hyperbolic, non-elementary, which means that the boundary of this telegraph has more than 2 points. Well, more than 2, which is the same as infinitely many. And the action of G on the telegraph is acylindrical. So, if you compare these three definitions, what you see is that this definition is probably the shortest one, and it's a beautiful definition to give, right? But it's the most useless one. I mean, it's useless for whatever purpose you want. The only thing it's useful for is for the purpose of defining the class. Now, if you want to check that some group belongs to this class, you normally check this definition, which is much weaker. Of course, 1 implies 2, that's obvious. But the fact that 2 implies 1 is non-trivial. Now, 3, this definition gives you much stronger condition, and if you want to work with an acylindrical hyperbolic group and prove something about it, it's much more useful. I mean, this definition is much more useful. It's even more useful than this one. What's the principal difference between this and this? Because here the action is co-bound. So again, the fact that 3 implies 1 is obvious, but the fact that 1 implies 3 is not obvious. One difficulty is that here we don't require the action to be co-bounded, while the action on the Kerry graph is always co-bounded. So first of all, given a non-co-bounded action, you have to produce a co-bounded action which is still acylindrical, and then of course you can use the standard Schwarz-Müller argument. So this is, I mean, all the equivalents here are non-trivial. Now let me list some examples. Yes.
So your generations are finite here then, or they could be infinite also?
Well, as if it's finite, then the group is hyperbolic, right?
Right.
If it's finite, then the group is non-elementary hyperbolic. So this is automatic, because that is geometric in this case. So in all interesting cases, the set will be infinite. Okay, let's talk about examples. So, for 10 minutes. Yeah. So let's talk about examples. The first example, let me rather say example number 0. So this class includes all non-elementary, or let's say non-elementary hyperbolic groups, hyperbolic, and even more generally relatively hyperbolic. Groups. So what does it mean to be non-elementary in this context? For hyperbolic groups, being non-elementary is just the same as being not virtually cyclic. For relatively hyperbolic groups, being non-elementary means that the group is not virtually cyclic, but that's not enough, because every group, well, it depends on the definition you use, but every group is normally considered to be hyperbolic with respect to itself. So you have to exclude this possibility as well. So a non-elementary relatively hyperbolic group is a group which is not virtually cyclic, and one of the peripheral subgroups is not the whole group. That's enough. So in this case, in the case of hyperbolic groups, the action on the locally finite Kerry graph is acylindrical because it's geometric. In case of relatively hyperbolic groups, the easiest way to see that they're cylindrically hyperbolic is probably to just use the definition by Brian Baldich. This group admits an action on a fine graph with some properties, and that action will be acylindrical, or you can prove that the action on the so-called relative Kerry graph is acylindrical. So in this case, we can actually verify the definition, and this is one of the few cases. I think it's one of the two cases which I know where the definition is, I mean, the fact that the group is acylindrically hyperbolic is proved by verifying the definition. Okay, number 1, and that's the first non-trivial example, mapping class groups, and this is a combination of results, so this is just trivial now, this is a combination of results by Mazur, Minsky, and Brian Baldich. So, mapping class groups of punctured closed surfaces, except the cases when GP equals, okay, what do we need to exclude? So we need to exclude the torus, right? And that's it in genus 1. And then we have to exclude this, oh, sorry, 1, 0. And then we have to exclude 0, 0, sphere with 1 point, sphere with 2 points, sphere with 3 points. Right? Yes? What? Oh, yeah, right. Why do we want to exclude those? That's right. Thanks. So, right. So it's just except 0, 0, 0, 1, 0, 2, 0, 3. So in this case, the mapping class group is just finite, right? So it cannot be acylindrical hyperbolic. Then if your surface is torus without punctures or with just one punctures, then the mapping class group is SL2Z, and then you are in this situation, right? And similarly, in case of the sphere with 4 punctures, then the mapping class group is Z2 cross Z2 extended by PSL to Z. So that's also hyperbolic, so you are in this situation. In all other cases, this is a so-called non-exceptional mapping class group, or non-exceptional surface. And in this case, it's known that the curve complex associated to the surface is hyperbolic. It's connected hyperbolic graph, let's say graph, we don't care about anything but one skeleton. And then that's resolved by, proved by Mazur and Minsky, and then Brian Baldich proved that the action on this curve complex is acylindrical. Next result is, well, I think it's this thing. Alpha 10 and at least 2. And now this is already much less trivial. So in this case, we don't know if there is any natural complex, which is like the curve complex for mapping class groups, for which G acts acylindrically. But we do know several constructions of some graphs. So again, I don't care about anything but one skeleton of some graph on which this group acts, and well, isometrically, the graphs are hyperbolic, and fully reducible elements act as lexodromic elements which satisfy the double EPT property. So the first such a graph was constructed by Langenstein and Fein specifically, so you fix a irreducible, fully reducible element. So an element is fully irreducible if it doesn't fix any proper free factor up to prejudice. And no power of this element fixes a proper free factor. So the first construction which they gave, you fix one fully reducible element, and for this element you construct a specific graph on which it acts in the way I described, and then they discovered that the same is true for the free factor complex, and then there are lots of other, now there are lots of other spaces in which this group acts, but there is none natural one. We know that there exists one from this theorem on which it acts acylindrically, but it's sort of not natural. We have to go through the general construction. Number 4, it doesn't need to be the next number. Just well ordered. Okay, so that's noticed in my paper. There's a short monocene, but it's actually based on the result by Wilton and Zalewski. That if you have the fundamental group of a 3-manifold, say closed, well, even compact, then you have to work a little bit, but compact, well, let's say irreducible. You can always assume it's irreducible because it doesn't change fundamental group. 3-manifold, then either G is virtually solvable, or M, this is my manifold M, is cipher fiber, or G is acylindrically hyperbolic. So in this case, if it's a closed manifold, you just take the action on the Bus-Serre graph associated with the J decomposition. It's not closed, you have to work a little bit, and the same alternative actually holds true for subgroups of 3-manifold groups, not necessarily finitely generated. If they are finitely generated, they are themselves 3-manifold groups. And of course, if your group is virtually cyclic, it cannot be acylindrically hyperbolic because it doesn't have 3 subgroups. And same can be proved in the case of cyclic fiber manifolds. the groups are not acyclically hyperbolic in this case. And let me mention a couple other examples. So that's number 4, right? Groups. Groups of deficiency at least 2. So if you have a finitely presented group which has presentation with 2 more generators than relations, it's acylindrically hyperbolic. So interestingly, I don't know an elementary proof of this. So the proof goes through using some analysis. In particular, what I use is some results about L2 basic numbers, which is a very strange way to prove something about groups of deficiency. Right? And finally, I want to mention cat0 groups. And there are lots of results you can mention here, but let me just restrict to the very particular case. So this is essentially due to Alexander system. In general, if you have a group which acts properly on a cat0 base and has around the so-called rank 1 element, then the group is either partially cyclic or is cylindrically hyperbolic. That's a general result. But if you project this to some familiar cat0 groups like rats, right angle Artin group is either a non-trivial direct product or cyclic or acylindrically hyperbolic. So if it's not cyclic and it's not a non-trivial direct product, it's acylindrically hyperbolic. So there are many other examples. For example, there are some interesting topological groups, connected topological groups, which are acylindrically hyperbolic. For example, the Cremona group, which is studied in algebraic geometry, and there are many other examples, but I think this list is long enough to convince you that this is a broad class of groups, right? So the next lecture will be about why lines are still not there.
All right, so we'll meet back in 10 minutes.